Okay, so today is going to be exciting. Trust me. So we're going to cover the full, from the three-level system all the way through to the equilibrium constant. So we're going to go through the internal energy, okay, the entropy. Finally, we're going to calculate entropy, enthalpy, the Helmholtz free energy, the Gibbs free energy. We'll talk about equilibrium constant. I'll show you examples of how you can have a spontaneous reaction be exothermic, how a spontaneous reaction can be endothermic, all driven by entropy, which is really just a measure of the partition function. So statistics is what drives these reactions forward. So it's pretty interesting. That's the statistics behind the phrase that Einstein was well known for saying. He's like, I just don't believe God plays dice with the universe. You may have heard him say that, and you may wonder what he was talking about. But there was some skepticism about quantum mechanics. Was this just some sort of what they call ad hoc, for this type theory for spectroscopy? Because all through the fall, all three of the four examples for the need for quantum mechanics were spectroscopy. There was the hydrogen line spectra, there was the UV catastrophe, there was the photoelectric effect. All of those dealt with light interacting with matter. And so they thought maybe quantum mechanics is just some boutique math trick to explain these things, and it really doesn't explain reality. The one that was not spectroscopic was the heat capacity. That if you cooled gases down, it started to drop below the classical value of 3/2 RT. And they couldn't explain that. Einstein actually did explain that by just a two-level system. Okay, so he said, wow, if I can calculate the internal energy of a two-level system, like we did last time, like we're going to do today, and the derivative of that energy is the heat capacity. If I cool things down, I don't have excited state molecules, and the heat capacity would go to 0. So that was one of his papers. He wrote it really quickly, like in a month. Okay, it's a foundational paper in thermodynamics and in quantum mechanics. But he saw the sort of the writing on the wall that this was going to lead to a statistical universe, and that's what he had a hard time accepting. But we can see through this development from that point forward of statistical thermodynamics that all of the properties that drove the Industrial Revolution, enthalpy, Gibbs energy, all of those were macroscopic properties, and that math would work, and those engines would work, even if you had no idea that atoms existed or molecules existed. It was just bulk properties. I heat up a gas, it pushes harder on a piston. I don't have to know that the gas is a smooth fluid or individual atoms. So it would work either way. But when you got into the quantum world, you realized that the atomistic view explained nature better, which is what we would call true. Okay. So it corresponds with reality. So let's look more carefully at the statistical thermodynamics. So we're going to connect that statistical treatment and the Boltzmann distribution to all of these thermodynamic properties. And so this entropy, let's focus on the statistical entropy. It can be described in terms of the number of states that are available at a given temperature. So that tells you it's related to the partition function. Boltzmann used that W for weighting factors. He weighted all of the different microstates, all of the different ways to prepare a system. And so he said there was a dominant microstate, basically the one with the most options is the one that is going to be the dominant one. And that's the one with the highest entropy as well. And so he developed this equation, S equals K ln W, and that's actually on his gravestone. So up there at the top, you see S is K log W. He used base 10 log, but still it's essentially the same thing in terms of mathematics. And so that's Boltzmann's tomb. He was troubled psychologically. I mean, he really was victorious in terms of his math related to entropy and explaining the ramifications of quantum mechanics. But he was still positing these particles known as atoms and molecules. And there was a whole philosophical movement at the time called positivism. Today we call it scientism. That the only way to know something is through empirical verification. And that any kind of theory that can't be empirically verified is just, not true. You can't say that it's true. And so they were hounding him over his atomistic views. And they think that their, criticism of his theories and so on led to his depression and suicide. Okay, so that's, it's okay to disagree, but don't hound somebody, right? Because eventually he was proven right. That just because you can't really see atoms and molecules, and we certainly couldn't in those days, in 1877 and the early 1900s, doesn't mean that your theory doesn't hold water. And that the theory suggested that these particles existed, but there was no real way to verify them. Until we got atomic force microscopy and we actually tap across a smooth surface and bump across the atoms and you can see them. And IBM famously pushed them around and spelled IBM in like the mid-60s with atoms, xenon atoms on a nickel surface. And so we've actually seen atoms now, seen by saying we've seen signals that are related to the atoms from an atomic force microscope. Well, Boltzmann's theory led to this statistical description of entropy. So now we understand entropy. How many times have you heard entropy is just a tendency towards disorder? And when we use that word tendency, we're really talking about delta S. So we're saying spontaneous reactions tend towards disorder. But entropy itself, like the entropy of a system, is just a calculation of the amount of energy levels that are populated and available. So that partition function is a measure of the entropy. You take the log of that partition function, multiply by the gas constant or Boltzmann's constant, depending upon the units you're after. And then you have the internal energy over temperature. So this is going to be a statistical entropy. Notice we calculate the internal energy first, and then use it and the partition function. Let me back up. We calculate the partition function first, use that to calculate the probabilities of those energy levels, and use that to calculate the internal energy. And then once you have the internal energy, you can calculate the statistical entropy using the partition function and the internal energy. Notice there was some other factors in here, and we'll talk about that later at the end of this lecture. But they essentially lumped into a constant C. And so let's do a problem. Let's focus on this problem for the whole class period. So this is a system of particles having 3 non-degenerate energy levels separated by an energy that is equal to the value of KT at 25 Kelvin. And I don't ever like using temperature from an energy level difference, but these are the kinds of problems you see in the book. So I wanted to go ahead and use this wording because I think it can be confusing. So there's the energy level diagram. And so so this is energy. And it's energy, and if you wanted the actual energy, you multiply these temperatures by Boltzmann's constant. So let's go ahead and do that. Let's just give it another energy scale. Let's do this in wave numbers. So if you multiply these numbers, like 25 Kelvin and 50 Kelvin by 0.695, $17. And so on this energy scale, we still have 0 there. This is 17. And so then this one would be 34. So 34, 17 wave numbers. So we could have just written this out in terms of wave numbers. Let's do this by joules, okay? It's going to be a really small number, right? Plus another 8, so 32. So if you had a scale of energy in joules, then this would be 0 still. This would be 3.45, and this would be 6.9. Energy divided by 10 to the negative 22. Okay. So we could, again, show, I'm just trying to show that you have this 3-level energy level diagram. And whether you label it with Kelvin, whether you label it with wave numbers, whether you label it with joules, you're really just picking different Boltzmann's constants to use. Okay, so there's really nothing peculiar about this kind of problem, but the wording is weird. So let's just look back at the wording again. System of particles having 3 non-degenerate energy levels. No problem there. 3 levels. Okay, separated by an energy that is equal to the value of KT at 25 Kelvin. Okay. Now you could calculate that and put 0, 17, and 34. Okay, or you could just label them 0, 25 and separated, right? So the next one is also 25. So 0 to 25 and then 25 to 50. If you can't get here, you can't do the problem. Right? This is the number one issue. You got text. Now what? Right? So you've got to be able to understand how to take the words and pull out the energy level diagram. So if you don't know how to get to the energy level diagram, then you're sunk at the very beginning. You know, you're tied to the dock. You're not going to sail anywhere. Okay. And we're kind of out of room, but we could also do joules per mole. If we're going to do joules per mole, what would we put here? Just the gas constant, right? 8.314 times this. So then you would get it in joules per mole. Okay. All right. So then this is the setup of the problem. Now calculate the molecular partition function at 25 Kelvin. So they're giving us the temperature of the system. It just happens to equal this temperature here. Okay. But our temperature, our thermal bath, the amount of energy we have is 25 Kelvin. Not very much energy. And so here's our partition function, but again, this is just made for the in-class example to make it really easy and quick so that you don't have to do a lot with your calculator, okay? So we have 3 terms. We have the ground state, the first excited state, the second excited state. So we have 3 terms in our partition function. So Q is equal to e to the minus 0 for the ground state, e to the minus 25 Kelvin over temperature, and e to the minus 50 Kelvin over temperature. And temperature is 25 Kelvin. So we could have used Boltzmann's constant in there for the energy levels. We'd have to use Boltzmann constant times our temperature, and the Boltzmann constants would cancel. And so that's why a lot of times they'll label energy levels with temperatures, because you have the temperature of the system. And so you just have 25 Kelvin over 25 Kelvin, or 50 Kelvin over 25 Kelvin. So you see this right here, this temperature of the system goes right there. And so that's why you have e to the minus 1, and then the next one is e to the minus 2. So when you add those together, you have 1 plus 0.37 plus something smaller than that, like 0.17. You end up with 1.503. So that's our partition function for this system at 25 Kelvin. If we were at a higher temperature, partition function would do what?
Equal partition.
If we went to really high, yes, then it would be 3. So it would approach 3 because we have 3 energy levels at really high temperatures. So this would increase above 1.5 as we raise the temperature, but eventually we get to such a high temperature that a difference in 25 Kelvin is significant. Right? And so we'd end up with a partition function of 3. We'd stuff all our molecules in those 3 energy levels, and it would be a 33% chance of being in any one of those. Yeah. And then if we cooled it down to 0, everything would be in the ground state, and we'd have a partition function of 1. Okay, so now let's take this and calculate that molar internal energy. Now that word molar is really important, because that's going to tell us what kind of units we're using. So rarely, in fact, I don't think I've ever seen it, wave numbers per mole. Okay, whenever we're talking about molar energy, we're dealing with joules per mole. Okay, you could do kcals per mole, but most of the time we'll just stick with SI units unless we're using wave numbers. Okay. And so here we have that the partition function. I've just repeated that calculation across the top. Then we have each of the probability terms, which is the individual Boltzmann factor piece over Q, plus the energy of 0, the energy of 1, and the energy of 2. So we have all three energies here, and we have the probabilities of those three. And so now, because we're dealing in molar internal energy, look what we're using right here for the energy, R. So R times the energy, the energy and temperature of those energy levels. So these are the energies of those levels. This is epsilon 0, epsilon 1, and epsilon 2. And then we have the probability pieces for all three of those. And so the algebra is simplified a little bit on the next line. When you put all that in the calculator, then you end up with 88.3 joules per mole. Okay. So then we have the internal energy, we have the partition function, and so we want to now calculate the average molar entropy at 25 Kelvin. So we need to know those equations. So you've got to find the entropy equation. If you have a note card, you're going to get S equals U over T plus R ln Q. And so since you have the internal energy, you're using that here. Using the gas constant, you put in your partition function here. It's pretty straightforward from here on out. You're just multiplying all of the different values. You have the temperature of the system, 25 Kelvin here. I've broken out both terms. The first term, U over T, is 3.5, and then the R ln Q is 3.4. So we end up with 6.92 joules per mole Kelvin. I want you to notice one thing about the entropies, and notice they still have that temperature in the denominator. Okay? The internal energy was just joules per mole. And if I have 4 moles, I multiply that by 4 moles, and then I end up with joules. So that's the energy in the system. But the entropy is always multiplied by temperature. So it has that Kelvin in the denominator. But we'll see later on with the H and A and G, these different energy components, that entropy is always multiplied by temperature because temperature causes entropy to increase or decrease. So we scale that entropy by the temperature of the system, and that corrects the enthalpy or the Gibbs energy or the Helmholtz energy. Any questions to this point? These get much easier with practice, and so this is something that you'll definitely do on the exam, just to kind of work your way through like a 3-level system all the way through and calculate USHAG plus the equilibrium constant. So, that it shouldn't be your first time to do one when we get to test day. That's going to be a bad outcome. Okay, so now let's look at the average enthalpy. So we need to go get that equation. So U plus RT. So the internal energy plus RT is going to be our enthalpy equation. We have S from the earlier, which we really don't need for the enthalpy. We have the internal energy. We have the temperature of the system. And so we have the 88.3 joules per mole. We have the gas constant times the temperature. So we end up with 296 joules per mole for our enthalpy. Now, when would we have a delta H? Notice there's no delta. This is just the enthalpy of this system. Yeah, so if we put this system in contact with another system, so this might be the reactant system and there might be a product system. Maybe the product system has degeneracy or something like that. Then we could take the enthalpy of the products and subtract the enthalpy of the reactants, and we could get delta H. You follow me? Yeah, so you have, if two systems are in contact with each other, then you can have a delta H. You can have reactants and products. And reactants don't have to be like two molecules coming together and exchanging atoms or something like that. It can just be two systems in equilibrium or coming to equilibrium, right? So it could be a system with 3 levels coming into equilibrium with a system with 2 levels. So this is the enthalpy. Now let's calculate the average Helmholtz energy. Okay, this takes the internal energy and adds in that entropy effect. Okay, so this is U minus Ts. So the temperature times the entropy term. And it's sort of a correction to the internal energy, taking into account entropy and the temperature. And so we have 88.3 joules per mole minus Ts, temperature times our entropy that we calculated. And we end up with negative 84.7 joules per mole. And once again, if we put this in contact with another system, we could do a delta A. And if delta A is negative, this is A, not delta A, but if delta A is negative, then it's spontaneous in the direction as written. Like if you have this defined as reactants and the other one as products, and you end up with a delta A that's negative, then it's going to spontaneously go towards the products. If it's positive, it's going to stay on the reactant side. So everything you know about Gibbs energy applies to Helmholtz free energy. I mentioned earlier what the Helmholtz free energy, what the conditions are for the Helmholtz. Can you remember what I said? We use Gibbs energy typically in academia, but in chemical engineering they use Helmholtz a lot.
Closed.
Yes, fixed volume. So a system of constant volume with variable pressure, that's the Helmholtz free energy. And a system with variable volume but fixed pressure is what we have in academia. We have, volumes can expand and contract in our glassware, but we have 1 atmosphere pressure. And so, things can leave the flask, can condense in the flask. We have, variable volumes, but our pressure is constant at 1 atmosphere, give or take. And so then lastly, the Gibbs free energy at 25 Kelvin. So this is G equals H minus Ts. So we have the enthalpy from the calculation, 2 steps ago. We pull that forward. We have the temperature, we have the entropy. And so our Gibbs energy for this system at this temperature is 123 joules per mole. And this is just G, it's not delta G. When we do Gaussian calculations and we get the thermochemistry output, that's also just G, it's not delta G. But if you take, say, oxygen and the hydrocarbon calculations, you can add those G's together and that's the products. That's the reactants, and then you can add up the amount of CO2 it would produce and the amount of water it would produce, and those would be the products. And then you could calculate your delta G and see if it's spontaneous or not. You can calculate your delta H and see that it's exothermic, because it's combustion. And if it produces more moles of gas than the reactants, it's going to be producing a large increase in entropy. So the combustion is got a hugely negative delta G, because delta S is positive, and if you notice the negative sign there, this G equation, G equals H minus Ts, also is the same equation for deltas. So delta G equals delta H minus T delta S. So if delta S is positive, meaning the products have many more moles of gas than the reactants. That's going to create a huge jump in entropy. So positive entropy change will lead to a negative delta G. And then if it's exothermic, delta H is negative too. So if delta H is negative and delta S is negative, you have a spontaneous process. I said that backwards. If delta H is negative and delta S is positive, then you have a huge spontaneous process. You have largely negative delta G. And so here's our summary of results. So that's why I call it USHAG. We have all of those values there for this three-level system. Now let's expand a little bit. Let's go from just a system that's describing one particle, or we've really been talking about moles of particles. There's one correction to that partition function that we need to make when we go to things like moles of particles. Okay, and so let's talk a little bit about the Gibbs energy. There are different forms of thermodynamic equations, and of course this is a whole semester course, what we've done in a couple of weeks. Okay, so we've skipped over a lot of the derivations. One of those is Stirling's approximation, and another is the statistical counting of the different ways to configure a system. There's a lot of factorials used in the statistical counting, and one of those equations for the Gibbs energy has this in it here, where we have the partition function raised to the number of particles. So if I have one particle, I can calculate the partition function. But if I have two particles or three particles, each one of those particles has its own partition function. So remember the Q's, it's the product of the Q's. And so it's product for water molecule 1 times water molecule 2 times water molecule 3. Well, that gets big fast, doesn't it? Because you have all of those water molecules, and so Q raised to the N is the number of water molecules in my example. But those water molecules are indistinguishable. So we're actually counting up too many, because it doesn't matter if I count water molecule 1 first and 2 second. I could have swapped you and get the same answer. So because they're indistinguishable, I need to reduce that number. It's too big. And so that's where this division of n factorial is. So that's to prevent overcounting, because we don't want to overcount. This is going to describe how spontaneous systems are and so on. So overcounting is going to lead us down the wrong path. So we want to divide out by n factorial, the number of particles factorial. Well, that's okay if I have 5 or 6 or even 10 factorials countable. But your calculator, like type in 100 factorial, see if you can do that. So find that exclamation point in there. That's the factorial function. And so factorial is just 1 times 2 times 3 times 4. So you can see how it blows up. You get to 5 times 5 and then times 6. You take each result and then you just keep multiplying by the next number. It's not emphasis. It's not saying 100. Okay, it's 1 times 2 times 3 all the way up to 100. And it just explodes. Okay, and your calculators can't even get to 100, much less a mole. And so Stirling's approximation is how we go from a small group of particles to moles of particles. Think about 10 to the 23rd factorial. Okay. Yeah, exactly. So and also the rules of logarithms, if you'll notice up here, we've got the natural log of a ratio. And so then that's a difference. So here we've taken this piece, minus kt ln q to the n, and we've pulled that piece out front. And because this is a fraction, we would say minus the other one, but this one's already minus, and so we say plus. Okay, so plus kt natural log of n factorial, and then we have this constant, the PV term is nkt, and so that's a constant there. And so this is what we're trying to get rid of, and we will use Stirling's approximation to get rid of that n factorial. Okay? And so that's Stirling's approximation right here. The natural log of a number factorial is approximated to this. Notice the factorial's gone. So it's the number of particles times the natural log of the number of particles minus those number of particles. Okay. And all of that times KT. And so we have KT times a minus n here and a KT times a plus n here. So those are going to cancel. So this piece here and that minus n go away. And so we have nkt ln natural log of n with no exclamation point. And we have nkt natural log of q. We could simplify these again. We could put that n back as an exponent of q. So this is how this simplifies. And then we can go back to that exponent, putting that n out front. But let's go ahead and take this nk and play with that for a little bit. N is the number of particles. Well, that's also the number of moles times Avogadro's number. So if I have 5 moles times Avogadro's number, I have the number of particles. And Avogadro's number times the Boltzmann's constant is the gas constant. And so this nkt right here is equivalent to nRT. And if I have this n times the natural log of those things, it can come inside as an exponent. And so this is the final simplification. I can move that, that little n out front and make it an exponent. I have the partition function over the number of particles. And so this is, even though you don't recognize it, this is something that's going to be familiar to us in a second. So this was just I wanted to go ahead and include this derivation, even though I skipped over many others in this course. I wanted to at least show you, we just used delta G was A plus PV, or we used G was, H minus TS. There's a bunch of different equations for delta G, or for G, I should say. And this is the one that's using that partition function. And we end up with this bottom result. So now let's make a reaction. Let's take the G for the reactants and the G for the products. Okay. So let's take a generic reaction. Come on, remote. So A times, A moles of capital A and B moles of capital B and so on. So this is a generic chemical reaction. When we calculate the delta G, what do we have? We have products minus reactants. So everybody should be good with this next step. We have the products C and D minus A and B. And we know the G's for each of those, the Gibbs energies for each of those. So I know this is like jumped ahead, but we have here the Gibbs energy for species C right here. Okay. And we have the number of moles there. And so those number of moles can be moved over here as an exponent. You see that? And the RT on all of these can be moved out front. And so I just have these natural log terms of the partition functions for molecule C and molecule D, molecule A and B. And again, I've got a difference in logs and a product of logs here. So when you add the logs together, that's a multiplication. And when you subtract the logs, that's in the division, that's in the denominator. They're all natural logs, so I can pull that natural log out front. And this is pretty amazing because delta G equals minus RT ln K. That is a value that we were able to determine before we even knew these partition functions. We were using concentrations and partial pressures to calculate equilibrium constants. And here we get exactly the same result using delta G's, or G's, Gibbs energies, that are based on a statistical treatment of the system. And we see mathematically where those exponents come from. And so that's a pretty amazing result. And you can rearrange this and solve for the equilibrium constant, that's delta G over RT. So again, we have the delta G of the reaction, and we have the temperature of the system scaled by Boltzmann's constant in joules per mole. So we see that similar behavior of Boltzmann's distribution, e to the minus energy change over RT. So it's all buried in that equilibrium constant. You've been using this really, I mean, it depends on your freshman professor, but sometimes they get into the Arrhenius equation in kinetics, and they talk about the probability of overcoming an activation barrier. That's Boltzmann's distribution. The energy of activation divided by RT raised to the exponent. So this has all been there the whole time. Now, one thing that we haven't addressed is the equilibrium constant used partial pressures, and the equilibrium constant used concentrations, like the molar concentration of this species raised to the number of moles, right? You remember that? And so those are just approximations, really. So this, whenever we look at the equilibrium constant, we've been using things like the concentration of C raised to the number of moles of C. And that breaks down. So that's telling you that's not the true value for the equilibrium constant. The partition function would be. But the partition function in a bulk system with liquid and all those intermolecular attractions would be too hard to calculate. But that would give the true result. And so for dilute solutions, essentially molecules in solution that are behaving like gases, they don't see themselves around, they're just diffuse around and they collide and they react. We're really kind of treating gas phase kinetics inside a liquid dense system. When the concentrations get too high, they start to break down. You start to walk away from what we would say that the errors in that partition function become significant. The nice thing about this equilibrium constant too, we have the partition functions on the top and the partition functions on the bottom. If any of those are off, they're probably off by similar amounts in the numerator and the denominator. And so the errors are gonna cancel, and that's why it does work to use concentrations. But whenever you have any one of the reactants or the products that's too concentrated, then its errors don't cancel by the others. And so then you get poor results. So the statistical treatment of quantized states explains the following observations. This initial failure of classical mechanics to see that the heat capacity would go to zero as temperature went to zero, that was not something we were able to address in the fall because we didn't get into the statistical treatment of energy levels. Okay, we were just looking at the spectroscopic examples. But it took all of this time after quantum mechanics. Now we can address that failure of classical physics and understand that the heat capacity would go to zero because the population of those energy states would go to zero and everything would be in the ground state. The entropy is really a measure of the density of states at a given temperature. Spontaneous change is driven statistically through the partition functions. And that equilibrium constant K depends upon those partition functions of the reactants and the products. And so you learn that these constant expressions were just approximations of the partition function. So the concentration of a species is an approximation of that partition function for that species, divided by the number of particles. And the same with the partial pressure. So if you've got a gas phase equilibrium going on, then you're really approximating those partition functions in the gas phase. Let's look at a couple of examples rather than take the Kahoot. So we can talk about responses to heat. We've got this pretty well understood. If you raise the temperature, you're going to populate more energy levels. But you see the energy level diagram, and you can see sort of this bar graph. This is the number of, this blue bar is representing the number of molecules in the ground state. And so this is, you see that exponential decay for the Boltzmann distribution. If we heat things up, you see it decays slower. And so you have more molecules excited. And notice the number in the ground state has decreased. So more are in the excited states. So that's your response to heat. Let's look at the response to pressure. Think about the particle in a box. That's why I like to teach quantum first, because we developed that theory pretty well in the fall. And so what happens to the energy level spacing when I shrink the box? What's that?
They get further apart.
Yes, because the length of the box is in the denominator. And so when it gets smaller, the delta E's go up. Okay? And so when we squeeze a system, especially a gas phase system, the energy levels get further apart. Okay? The partition function actually drops. Okay? This idea of density of states, I use that term. So you've got a range of energies, like if you say, 7 joules, you've got 3 states in 7 joules. If I had another system that had 5 states in 7 joules, that would be a higher density of states. So you sort of pick a band of energy, how many energy levels are in there? That's what we're talking about, density of states. Another way of saying how close are the energy levels together. And so you'll see me talk about density of states quite a bit. Now, this is a graphical representation of equilibrium constants. Notice the gray on the left is the reactants. Okay. And the blue on the right is the products. Start there. You follow me? Okay. Then you've got the energy levels. And you've got the Boltzmann distribution, or the Boltzmann factors for each of those energy levels. The probabilities of being populated in each energy level. Now, this is the thing that you've got to get across. You can only have one 0 on the energy axis. So you might have the products be a higher energy than the reactants. And so the lowest energy level in the system is 0. Everything else is above 0. So in this case, all your reactants start there. That's the minimum energy for your reactant molecule. How would I calculate that? Well, Gaussian would tell me that. It would tell me which one of these molecules is the lowest energy one. And so that lowest energy molecule, or if I had 2, I would add those together and that would be my 0. And then the products would be higher in energy. And so this would be delta E between the 2 Gaussian calculations. And then on top of those, I'd have all of the rotational excitation and vibrational excitation for those molecules. Now I could put them in contact. What do I mean by contact? Well, I just use one Boltzmann distribution to calculate all of the populations. And what I see here is, notice ground state for the reactants, first, second, third, fourth excited states, right? But before I get to the 5th excited state of my reactants, I've got a product here. And look at the width of that bar. It's intermediate between this one and that one. You see, once I get of that 4th excited state, then I'm calculating the probability of being a product. And then another reactant, and then more products. And then I sum up all of these. I can add all of these together, and I could subtract all of these, and I could see what my population would be. Does this equilibrium favor the products or the reactants? And in this case, it favors the reactants. You see, so this is endothermic, and the equilibrium lies to the left, the reactants. If I add up the probability of being a reactant versus the probability of being a product, the probability of being a reactant is much larger. But look what happens with density of states. See how many more energy levels I have in the products? Even though it's endothermic, this is the reactants. This is the products. This is probably a situation where the products are gaseous. And the translational energy differences are really close together. And so I calculate the Boltzmann factors. This is obviously the most probable in any given energy level. But then I'm in the products and I calculate that next one, the next one, the next one. Then I get to here, then I jump over and I calculate a reactant, and then a product, reactant, product. And then I look at all of the, you could say, what's the partition function for the products? It's all of these added together. What's the partition function for the reactants? It's all of those. If I take the ratio, I get the equilibrium constant. And that's going to be greater than 1. I have a higher probability of being a product molecule than a reactant molecule. And nature's just doing this. You have this energy level structure based upon the container, the temperature and everything, and you throw your molecules in, and it's musical chairs. And they sit where they sit. And they bang into each other, and one may drop down here, and one may jump back up, and so on. But this is the equilibrium state that's defined by the Boltzmann distribution, and here you have an endothermic reaction that's spontaneous. So it's, hopefully mentally you can see that statistics is driving all of these equilibria. We really can't, we don't have the computational power to do this in condensed phases like liquids. We can do this in gases. So we can put together computational programs and Gaussian and so on, and we can calculate the partition functions and do gas phase equilibrium calculations, which confirms that the math is right. We just don't have the computational power to do that many interactions of molecules. And it's also very difficult to understand. If you've got a water molecule inside a liquid, is its volume really a container, or is it a little cage around it? So that it gets ambiguous as to how to define the volume of a molecule in a liquid state. And then when it vibrates, one molecule vibrating against another is that a translational mode or is that a vibrational mode? So that gets a little fuzzy too. So it's very difficult to calculate condensed matter, and you'll see condensed matter physics being a big field. But anyway, this is the conceptual example I wanted to get to today, so that you could see how, even statistically, an endothermic reaction could be spontaneous.